Get over there. Okay, cool. I need to show over there. Okay. Ooh, here we go. So, like today in class, we're doing a problem, well, two problems, where we're having light pass through some sort of medium. In this case, it's going to be glass. And then another beam of light of the same frequency and wavelength not passing through that medium, and we're trying to find the certain amount of like minimal thickness, second minimal thickness, something like that, of that nature, that will give either a bright spot, which is either a bright spot or a dark spot. So either constructive interference for a bright spot or destructive interference. So I wrote out the problem that he the kind of formula that he put up today. And for this like simple type of problem, all we're gonna have is the number of waves that occur in the medium. So these two are the number of waves for the top beam here, and the minus in waves in air is the bottom. So this part here is the number of waves that is in the medium, and then plus number of waves out of the medium gives you the total number of waves for that top beam. And then you just have the number of waves in the air for the bottom one. It's a lot more simple. So the formula he kind of gave for that was x, which is the thickness. He labels it x. He could have labeled it t. But x, which is the thickness, divided by the wavelength of the medium, plus the total distance minus the thickness, which gives you the rest of the distance after it passes this glass, divided by the wavelength in air, since it's in air the rest of the time, minus the distance divided by the wavelength in air, since that's what you have for the bottom beam here. So, and if you realize that, I don't know if you have, you can actually simplify this equation by spreading these out, and you end up being able to cancel two of them, and what you actually end up with is just x divided by the wavelength in the medium minus x divided by the wavelength in air. That's what the entire thing simplifies out to.
Wow.
Yeah, isn't that great? And that equals the, what I labeled as m, I don't know why I did, I just did, which equals the number of wavelength difference that you're trying to find. So for like the minimal thickness that'll give you constructive interference, it will be 1, because that's the amount of wavelengths that you, the amount of wavelength difference that you could have and still have a bright spot. Okay? So the two problems that we're doing today are with this sort of layout here, and we're doing it with a frequency wavelength light of 5 times 10 to the 14th hertz. And doing the, C equals, not C, sorry, wavelength equals C divided by F. We end up with a wavelength in air. You always need to find the wavelength in air. That's helpful. And the wavelength in air is 600 nanometers, or 6 times 10 to the negative 7th meters. And then it'll also be helpful to have, obviously, the wavelength in the medium, and since n equals 1.5 for glass, our lambda in glass will just equal 600 nanometers divided by 1.5, which just equals 400 nanometers. Now all we have to do is just plug it into this lovely equation over here. So write out the entire equation. Oh, and then we also want to first find, the thing that we're trying to find first is the second smallest thickness of the glass that will give destructive interference. Okay, so second smallest thickness, right over here, second smallest T,
Destructive.
Okay, second smallest for destructive. So if they start in phase, which is what we've done the entire time so far, if these waves start in phase, then the smallest thickness that will give us a destructive interference will be half of a wavelength, or 0.5. And since we're trying to find the second smallest, all we have to do is add 1 to that, so 1.5 will be that m in this equation I've written over here. So I should probably move this way.
Can we use that reduced version?
Yeah, that's totally fine. I'm going to write it out without the reduced, but then the second time I'm not going to. So x is going to be, so we just do x divided by 400 nanometers equals, not equals, what am I doing? Plus d, which we already have, is 12 minus x divided by 600 nanometers minus d, which is 12. These are meters, but 12 meters divided by 600 nanometers equals 1.5. So if you're going off the equation that we did in class, this is how you'd write it out. X over 400 nanometers plus 12 meters minus x over 600 nanometers minus 12 meters divided by 600 nanometers. If you really wanted to get specific, you'd probably have to make everything either in nanometers or in meters, but as we can see by doing that equation, what you actually end up getting is just x divided by 400 nanometers minus x divided by 600 nanometers equals 1.5, because you'll end up with 12 meters divided by 600 minus 12 meters divided by 600, so it's just going to cancel. So lucky us, we don't have to deal with that. So what we end up with is 1 over 400 times x minus 1 over 600 times x equals 1.5, and if you do that on your calculator, you end up with something like 8.33 times 10 to the negative fourth x. This is nanometers. X equals 1.5. And then solving for x, what you'll end up getting is x equals 3,000 nanometers.
How'd you get to the negative point?
So if you do 1 divided by 400 minus 1 divided by 600, you'll end up with this number. And then if you just do 1.5 times that number, you're going to end up, or 1.5 divided by that number, sorry. 1.5 divided by that number, you're going to end up with 3,000. You just have to keep in mind that this was done in nanometers. Okay? Okay, so the answer, was actually, oh, sorry, it was not 3,000. What am I doing? I did the math wrong. I put down the wrong answer. I did all the math right up to this point. 1,800, sorry, 1,800. 3,000 is the answer for the next one. Surprise, surprise. Yeah, so if you end up doing all this math, which you can kind of just simplify as this to start with, you end up with x equals 1,800 nanometers. So that is the second smallest thickness of the glass in this situation that will give a dark spot or deconstructive interference 12 meters from the original spot. 12 meters from the original point the light is coming from. Okay?
Cool.
Okay, so the second one is slightly more tricky, just kind of conceptually. The math itself is not any art. So I'm going to keep everything else up, because everything else is staying the same. So for the second problem, we're going to have the same distance to start with. Like I said, I never put d up. D equals 12 meters. So we're going to keep the same frequency, the same glass with the same N value, all of that. But now we're going to be looking for the third smallest thickness for constructive interference. But this time, there's a twist. We're going to start with out-of-phase sources. Okay? So starting with out-of-phase sources basically just means we're going to shift everything by 1/2. Okay? So everything that would normally give a constructive interference if they start out of phase will now give a destructive interference. So if you add this equation equals m equals 1, which is normally constructive, you'd have destructive because it started destructive, and a shift of 1 wavelength will just give you destructive interference again. So if you have to shift it by 1/2, you basically just take all of those numbers you usually have, 1, 2, 3, and then subtract it by 1/2. So now the smallest thickness that you could have for destructive interference or for constructive interference would be 1/2 of a wavelength. Okay? It's kind of confusing to like do that. Does everybody understand?
Because it would have been 1, but you had to subtract.
Yeah, but now you have to subtract 1/2 a wavelength because they start 1/2 a wavelength out of sorts, basically. Okay? So they start already 1/2 a wavelength out of phase. So completely out of phase, and you want to make them end up in phase, the third thickest. So to do that, to get the minimal thickness, you'd just use 0.5. Second smallest, you use 1.5. Third smallest, 2.5. So do the exact same equation. I'm just going to write out the abbreviated form this time. So x divided by 400 nanometers minus x divided by 600 nanometers equals 2.5. Okay, so 2.5 wavelengths is the third thickest amount, third thickest amount for that glass. That will give you constructive interference because they start out of phase. Okay. So doing this once again, we'll just end up with the same thing over here: 8.33 times 10 to the negative 4th meters times x equals 2.5. That's you. And solving for that, like I already said, x equals 3,000 nanometers. So the only real tricky part of this was just figuring out what this value of m that we have is.
Can you go through that again?
Yeah, definitely. Okay. So it'll be the same math every single time. So no matter what the situation is, this equation is going to stay the same.
Finding the m.
Yeah, so finding the m. So normally, if I said find the second smallest thickness that will give destructive interference if they were starting in phase, what would you say? What would be the m number? Second smallest if they start in phase to give destructive. What did you say?
1.5.
Yeah, 1.5, 1.5. Okay?
So, isn't it you go by 0.5 when you want it to be destructive?
Yeah, you actually go down 1/2 for this. Yeah, so if you notice, like normally constructive will equal 1, 2, or 3, or it could equal 0, but obviously we have shifting here. So and then destructive will equal 0.5, 1.5, 2.5, etc.
But that's just for in phase waves.
Yeah, and so this is for in phase. So for in phase, the lowest number that you could have if they are not just in phase the entire time, if there is a shift in wavelengths, is 1 wavelength. We'll still give them in phase. Destructive, they only have to shift 1/2 a phase to get completely destructive, or 1/2 or the other. This completely flips, so I'll just write out flips. So this is for in phase. So out of phase. Constructive will now be just the opposite. It'll be 0.5, 1, 0.5, blah, 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 and then destructive will equal 1, 2, and 3. Because since you already start, so now out of phases, you start like 0.5. You basically start at 0.5. You already start 1/2 wavelength out of phase.
Was it the third thickest for the one we just did?
Yeah, the third thickest. So 0.5, 1.5, 2.5, what happened next? Yeah, so this was third thickest. No, yeah, we're good. So does everybody understand why this is the way it is? How we find that number for what I'm calling m?
So in a question, it could be like in phase and then You could say like, what's the second smallest for out of phase? Like,
Yeah, so it'd be like
before?
if so he could have asked something like basically like we just did, so like the first problem. So like for this situation with beams of light starting in phase, what is the second smallest thickness they'll give destructive, interference or something like that. And then in the next like question, he might ask something like, in the previous example with light starting out of phase, what would be the third thickest that would give constructive interference? That's how he'd probably word a test. So he'll have to
So if
say
say we
in or out
started
of phase.
at like m equals 1 in phase, and then the second one was like out of phase, you'd use m equals 1.5.
It depends what you're wanting. So if you're saying like the second smallest, so let's say we're saying second thickest that'll give constructive for both. So if it's second thickest for constructive and they start in phase, then you just go from you can even write these down and just go off of this. So the first thickest would just be 1 for in phase,
Yeah.
and then second would be 2. But if they start out of phase, the first thickest is 0.5 and the second is 1.5.
Okay.
Yeah, write down these.
Okay.
It'll help.
When you said second thickest or second smallest,
Second smallest, yes.
so you just go down the line.
Yeah, yeah. So yeah, you can only find like certain increments. Everything.
Second thinnest.
Yeah, thinnest.
Second thinnest, not second thickest.
Yeah.
Yeah.
Second minimal thickness.
Second.
The
Yeah,
other issue
second
with
thing.
was like if you let's say you're in phase at 1.5, right?
In phase,
You want to go
1.5.
you want 1 point. You could either be at 0.5, 1.5. Wait, what are you talking about? For it depends. There's tons of different situations.
Let's say like you start in phase at 0.5. I didn't mean to say 1.
Yeah, So you're starting out of phase.
Yeah,
Yeah.
and then you get like once like the question asks, okay, starting at in phase at 0.5.
You can't be in phase at point.
Yeah, you can't be in. Yeah, out of phase is you're basically already shifted 0.5. That's because out of phase you're shifted half a wavelength relative to the other one. That's
In phase is whole numbers.
Okay.
Out of phase half numbers.
Okay then.
Yeah.
All right.
Yeah. That's exactly right. Cool. Any more questions?
That's what I.
Are we always going to subtract 0.5?
You always do the smallest. So like if you added 0.5, you'd start with 1.5, and you
Yeah.
could have a small
Yeah, I
one
get
at
what you're
0.5.
saying.
So that wouldn't really work well. So
Okay.
so basically start at the smallest possible thing. So if you could think, okay, could I shift half a wavelength? And you're like, yes, of course you can. So yeah, it has to be the smallest possible that you could have.
Okay.
So yeah, I think whatever that may be. Anybody else? Is everybody else good? Okay, that's what we're doing today.